So yeah, we've got a group of people here, and we'll see how many people connect up remotely. Always a gamble, what's going on and what people are doing. Thank you so much for being part of this. Ahmed is hiding somewhere, so I'm James Allen. I don't know. You don't. The problem with everybody here is you don't have our names in a little box underneath our picture. It's actually. So I'm James Allen. I'm actually sort of talking to everybody here and to whoever's remotely here, I guess. So I'm the director of the Center for Intelligent Information Retrieval, and this is many of the students and staff from the CIIR as well as other guests. We're delighted to have you come here. So our speaker today, well, actually, one thing before we get going, can you share your screen so we can make sure that's working?
Yes, that's correct. Let me see. Okay, and can you see my screen?
Looks beautiful, yeah. Okay. I'm going to bet it's not that cold in Virginia right now.
No.
Okay, so our speaker today is Ismini Lourentzou, who is going to talk to us about visual understanding with limited supervision and doing it in a robust way. She is an assistant professor at Virginia Tech, where she runs the Perception and Language Lab. The focus of her research is sort of combinations of machine learning, AI, and various things, typically trying to look at interesting database problems, as many machine learning problems are, with, I think, an emphasis on multimodal data in a lot of cases. So not pure text, not pure images, but things that might bridge these areas in interesting places. She's not only at Virginia Tech, but she has an affiliation, actually it's on here, with this Zamani Center for Artificial Intelligence and also the National Security Institute. So she's got a wide range of affiliations. She's also one of the organizers of NeurIPS, I think both 22 and 23, and also is, I think, leading a group or that is another one of the Alexa Prize folks working on the TaskBot Alexa Prize. Which some folks here are familiar with through the stuff Ahmed has been doing. Without further ado, Ismini, please take it away and tell us about robust visual understanding with limited supervision.
Thank you everyone for inviting me to give this talk. It's great to be able to talk to UMass CIIR students and faculty. So a brief overview of my group. I lead the Perception and Language Lab, or Plan for short. We're interested in multimodal task assistance that combine vision and language modalities. And we work on several tasks such as healthcare, video understanding, body AI, and self-supervision. So we've come a long way in deploying AI machine learning models in several domains, from wearable devices, smart agriculture, digital health, and many more. And two of the key ingredients for training high-performance models is the better computational infrastructures and the large amounts of data, training data, that we have in our disposal. And these two ingredients have led to an exponential growth in terms of model capacity. So we went from language models that have millions of parameters to models that have billions of parameters just in the past few years. However, data in the real world is not always as well structured or ready to use as these models would like to. So, for example, I have two domains here. I have image segmentation and entity recognition, name entity recognition, and we can see that both of these tasks require fine-grained labels. And in general, it is difficult to understand the visual world without annotated data. Thankfully, there are new directions in learning with limited amounts of annotations that can now enable better visual language understanding. So in this talk, I will cover a few of those directions. First, I will cover self-supervision for tasks such as image classification or text classification. And then I'll move on to web supervision for more complex tasks such as video understanding and video summarization. And in the end, I'll follow with embodied AI. This is one of the directions that my lab is very interested in for the future. And you can learn a lot about our lab's work in machine learning for health from our publications. Okay, so feel free to interrupt me to ask for questions, although I cannot see the chat, so please feel free to let me know if there is a question. So we'll start with self-supervision. So what is self-supervised learning? So self-supervised methods are methods that try to transfer knowledge from some kind of auxiliary task that we can learn on unlabeled data. And we typically get labels for free because these are parts of the sample. So these tasks are simple to formulate, but require understanding of the context. So for example, it might be try to predict the next word or predict a sequence of words in a sentence. So masked language modeling, for example, is this kind of way: predict randomly remove a word and then try to predict what was the word. And in these cases, we don't care really about the performance on this task, on the auxiliary task, but we care about the representations that we learn. And we hope that these representations will encode the structural or semantic information that could be beneficial to a variety of tasks. One of the growing communities in self-supervision has to do with contrastive learning. So contrastive learning tries to create an auxiliary task where we create differently augmented views of the same sample, and then we try to minimize the distances of the similar examples. Let's say here I have a dog, I have two different augmented views. So I'm trying to minimize the distance of these two different augmented views of the same sample, and then I'll maximize the distance of dissimilar negative samples. And this has shown to even surpass supervised performance in some cases. But you can see that the loss that that for example, CIIR loss, one of the most popular ones, it requires sampling a set of negatives to compute the denominator. And there has been a lot of work that shows that this kind of negative sampling can actually lead to performance drop, because in many cases we do not know what is the actual negative sample. So every example with its, every differently augmented view of the same sample is treated as negative, but all other samples are treated as every augmented view of the same sample is treated as positive, but all other samples are treated as negatives. So we might sample somewhere like a false negative. So most of the methods will try to design various sample selection, negative selection mechanisms, and these are typically, you can think of them as important sampling. So let's take a look at what are the main challenges in finding representative negative examples. So first of all, the negative examples should be somehow hard examples, right? They're not easy examples to learn. So they should share some kind of similarities with the anchor. So their feature representations should lie close to the anchor representation. Secondly, we would like to avoid, as I mentioned, false hard negatives. So samples that have the same class label as the anchor, but those are again very close to the anchor. So in the absence of no label or the absence of class information, we have to rely to some kind of unsupervised strategies to filter these false hard negatives. And also, we would like to find a set of negative examples that represent the diverse data distribution. So a selection mechanism should ideally capture all the three properties: anchor similarity, informativeness, or let's say influence, and diversity. So here we present the method where we take a set of examples in a batch, and we have, let's assume that the dog is a positive example. We create two differently augmented views of the positive example with the anchor, and then we have a set of examples that we can use as negatives. So in the beginning, same as previous methods, we will use anchor similarity. So we'll just calculate the pairwise similarity of this positive example with all other examples in our negative pool. And then we want to find examples that are more influential, meaning that we want to avoid false hard negatives. And we also, but in order to avoid these false hard negatives, we should have some kind of decision boundary. So we could use model confidence. But in our case, we do not have class information. So if you read our paper, we have an auxiliary task where we create a pseudo labeling task, and then we use a model confidence or model chains by each example. So for example, here, the cat example, how much did change the model, this negative example. And then we use gradient similarity, because this gradient similarity essentially codes how influential this example, this negative example is with respect to the anchor. So by looking at the gradient differences between the anchor and the negative example, we can look at how influential a negative example is. And then we want to also find diverse examples. One way would be to just do clustering, but this is very computationally expensive. So we resort to some approximation, which is just comparing the average distance of one example from all other negative examples in the embedding space. So these three different metrics essentially gives us different important sampling mechanisms for the negatives. And then we can combine them with an attention-based method. So we learn these lambda parameters of which of those metrics is more important for a given task. And then we create an aggregate score that we then use for negative sampling. So for visual representations, we evaluated on 3 different domains. So we evaluate on visual, text, and graph representations. Here I have the visual representations. We have in total 3 image tasks, so CIIR 10, CIIR 100, and Tiny ImageNet. And we can see that for top 1 accuracy, our method surpasses previous negative sampling strategies. And if you read the paper, we have a lot of qualitative examples on the visual domain. But we can also see large improvements also for text. So here we have 6 different text classification tasks. And we perform 10 cross validation for binary classification, and the others we just do multiple trials. And we can see large improvements in several of those tasks. And we also have qualitative examples. So if we look at in the top row, we have a baseline. In the bottom row, we have our methods. The anchor in the first example is a bird. And then our method samples more diverse examples. So here you can see that the baseline has sampled 2 negatives of the same class, trunk. And it also sampled a false negative example, so another bird. But our method tries to sample a diverse set of examples and avoid false negatives. So you can see here that in both cases, we avoid false negatives, and we have a more diverse representation of the pool of examples. And we have a lot of more qualitative examples in our paper. And you can find the link here, and there's also like a QR code if that helps. Okay, so now we have already found a way to sample negatives, but there is another problem with these self-supervised methods, and that despite the recent advancements, there hasn't been a lot of work in adversarial learning. So in many cases, these neural models are brittle when we give adversarial examples. So there has been a lot of work in adversarial training that shows that when you have an image and you impose some small perturbation, some small perturbation that is constrained within a certain radius, and you design that perturbation so that it is adversarial, meaning it tries to maximize the model gradients, then you can make your model misclassify a lot of examples. So we want to train models that are self-supervised, right? But they also are robust to this kind of attacks. And these attacks are usually, as you can see, undetectable to human eye. In the case of traditional adversarial training, what we do is usually In the case of adversarial training, what we do is usually we just try to find the perturbation that maximizes the cross entropy loss, but that means that we require to have class labels. In the case of self-supervised learning, we do not have class labels, and there are many methods that just straightforwardly replace the cross entropy loss with the self-supervised loss, the contrastive learning. And these methods try to maximize the contrastive learning, try to find the local perturbation that goes towards the direction that maximizes the contrastive learning gradient. But in that case, you can think of this kind of attacks as untargeted, right? So the model the perturbation that we will devise tries to confuse the model to misclassify an example as any other label. Right? Because we treat all the other examples in our pool as negatives, and we treat them equally. But it would be nice if we could design some kind of targeted attack, which you can do if you have class information. So it would make more sense to try to misguide the model to misclassify the cat as a dog rather than a teddy bear, and that will be a more difficult attack. So in our case, we want to design pseudo-targets that are induced by clustering to explicitly guide the perturbations in a self-supervised setting. So what we do, we first have these examples, we cluster them, we create differently augmented views of the same sample, and then we permute the pairs so that we can design examples that we can design pairs that have the same class or a different class. So first we permute, and then we assign an indicator variable according to whether these two instances in the pair after perturbation belong to the same cluster based on the clustering that we have done, or in a different cluster. So we call the ones that belong to the same class a positive pair, and the examples that have a different cluster as a negative pair. So here, for example, after my perturbation, I will have two instances of a cat, and then that is a negative pair. But if I have a dog and a cat, that is a positive pair. So after we create this kind of pairs, then we utilize this indicator variable to guide the sign of the gradient when we design those perturbations. So we want to essentially maximize the contrastive loss for positive pairs, meaning that we want to create perturbations that bring those same class examples further apart. And we want to minimize the contrastive loss for negative pairs, meaning that we want to design perturbations that bring these examples closer. So those perturbations will be adversarial. We try to fool the model to misclassify, for example, the dog as a cat. Once we have these perturbations, we just add them to one of the examples in the pair, and then we match the examples back to the corresponding original alignments. And then we perform the contrastive training, same as before. So we have results on both white box and black box attacks. Here I just present the results with the PGD white box attacks on CIIR 10. We can see that there are several methods that are categorized. So for example, supervised learning with adversarial training methods, self-supervised with no adversarial training on the second row. The third one is adversarial and self-supervised methods previously in the literature in comparison with ours. And then there is also a robust evaluation. So we can see that, and I have color-coded to indicate the best performance in each category. But in general, we can see that when we add these attacks to the model, that the performance on clean images, so the first column here, degrades a lot. But our method tries to balance the trade-off between performance on clean data and robustness to adversarial attacks. So in the two columns, I have seen attacks, meaning that the model has been trained on those attacks. And in the remaining columns, I have unseen attacks, meaning that the model has been trained, for example, on L infinity, but when during testing, it sees an L2 attack. So we can see that our model is better on L1. So those are more constrained attacks, but it is somewhat comparable with the rest of the methods in the other attacks. We also performed experiments with several other white box attacks, such as BIM, Jitter, and FGCM, and those are unseen, meaning that the model has not been trained on these attacks. And we can see that in general, our method shows better performance across the baselines, against the baselines. And finally, we perform a qualitative analysis, and we visualize the clusters for CIIR 10 for all of the methods. So there are 10 classes, and each of them is represented with a different color, and the legend shows the label information. So we can see here that our method produces more well-separated clusters. So I'll briefly stop here and ask if there are any questions. Okay.
I wonder, on this last thing, this is a qualitative in the sense you're just showing us a visualization of a simulated annealing or something. Did you actually look at like how tight the clusters are quantitatively, like the average distance between the members of the clusters?
That's a good question. We didn't look at qualitatively how tight the clusters are, but we can certainly add that to our paper. Yes.
I mean, it's pretty clear something happened.
Yes, but qualitative analysis wouldn't hurt actually. It would probably give us a more understanding on the clusters that appear to be a little bit more dispersed.
Good. Thanks.
Thank you. Right, if no other questions, or you can ask me later, I will continue to the next one, which is to learn with web supervision. So in many cases, we have information available from the web that we can retrieve in order to complete a task. And in this chapter, I will go over video understanding. And now you may ask, why video? Well, it's not hidden that there has been a lot of more and more users that are creating and uploading videos on platforms such as TikTok, YouTube, and many more. And there has been an explosion of video than ever before, with users spending at least 7 hours per week, and that was in 2019, on just watching video. And most of the average consumers, the US consumers, have at least 4 video subscriptions. So we have growing amounts of video that we get to watch. But the question remains on how can we efficiently browse, search, and index video content. And compared to just labeling an image, whether it contains an object or not, annotating video data, especially for fine-grained tasks such as video localization or video summarization, it's a very tedious task. And we have very limited annotations for specific domains. So in many cases, we could use self-supervised learning, but most likely we would need to have additional information that we can use to perform this task. And there exists a lot of useful information in the web that we can retrieve and utilize. So in this talk, I will focus on video summarization. So given that the user is interested for a specific event and they don't want to watch all of the videos, they just want to quickly grab a summary. So our goal is to create a summary from multiple videos. And a summary can be thought as a subset of the input video frames. And the criteria, we want it to be concise. We want it to be representative of the query relevant events. So when the user asks about the Prince William wedding, they care more about the event of the wedding. And of course, we want something that is chronologically sound. We don't want the user to see, for example, walking down the aisle after the wedding ceremony. Now, previous methods in the literature have mostly multi-stage pipelines to optimize this criteria. So, for example, to create a concise summary, we might select a set of diverse frames, and then after you have these frames, you can discard irrelevant ones by looking at images that you retrieve from the web with the same query. And then you can order frames chronologically after you have selected the frames that you want to add to the summary, and then you use, for example, some timestamps or topic closeness or frame closeness to order them chronologically. But the problem is that this is not end-to-end, and especially when we're looking at these pairwise similarities and the clustering, those have polynomial complexity with respect to the number of input frames. And of course, there is a lot of error propagation through the sequential stages. There isn't something that you can learn end-to-end and improve all of the different steps. So in our case, we propose an end-to-end model that factorizes the information of different modalities into 3 attention-based distributions. And those attention-based distributions, the video attention, the image attention, and the query attention, are then combined to compose the final frame distribution. So briefly, we have the web images that we have retrieved from the web, and then we also have the query and the video titles and the descriptions as the text data. And then each of those videos is a different attention mechanism. And those are, again, combined in a hierarchical attention that combines all the video information. So once we have this hierarchical attention and the image and query attention, we can just use a pointer network to select from that distribution and start gradually building our summary. So we perform experiments on a data set that has several different queries. So there exist 10 events. Each of them has a varying amount of videos, and we want to create one summary, one coherent summary across utilizing these videos. And they also have a varying amount of web images retrieved from the web. And in the end, we have user summaries from 4 different users that we can use for evaluating our methods. I will not go into details about the qualitative results. You can take a look at the paper. Here is the link, and again, a QR code. But in terms of qualitative analysis, we compare with, in the first row, we have methods that just operate on one video. So what if we treat all of the video frames across all videos as a single video, and then we use, for example, clustering to create a summary, or other methods in the literature. In the second row, I have methods that are multi-video summarization, and then we have ours. So I have the red are noisy frames that are irrelevant or not useful. As you can see, they're just random noise. And the yellow are frames that are redundant, meaning that, as you can see here, this frame is sampled twice. And you can see, compared to all of the previous methods, our summary sampled only one noisy frame, but it didn't sample a lot of irrelevant ones. So this is just one qualitative example. We have a lot of analysis in the paper, user studies, more information about how we built this model. But before I conclude, I would like to move on to the next task, which is learning with learning for embodied visual navigation and task completion. And I think this would be a very interesting future direction for our lab. So we went from visual language understanding for tasks such as medical question answering or video summarization to more intelligent embodied agents that can accomplish various tasks through navigation and interaction with the environment. So, for example, in here I have an instruction that tells the agent to navigate to a goal location, Or in the other example, I have instructions that tell the agent to rinse the cup and place it in the coffee maker. So the agent has to navigate to certain locations and also manipulate multiple different objects in the environment. So there has been some work in Embodied AI, of course, actually a lot of work. And most of these works try to build agents that can understand human instructions and then actually perform the task. So navigate to co-locations, being able to understand the physical attributes of objects and how actions affect those attributes. But there has been very limited work on endowing these agents with the ability to ask questions, receive feedback, and adjust their plans. There has been some work that uses oracle answers for training interactive agents, and those usually involve navigation tasks because we can easily find the next best step in those cases. So there is some ground truth that we can utilize to have an oracle to design template-based solutions. But here we're interested in free-form question answering, to incorporate free-form question answering so that the answers and the questions are not constrained. And also we are interested in more complex task completion environments. So here I have our method, which is called embodied learning by asking. The goal is to complete tasks in a household scenario. So for example, boil a potato. Our first step will be to have a planner that tries to decompose the instruction into future sub-goals at the current time step. So we have an observation that is a visual observation of the space. We utilize this to create different sub-goals that the agent should tackle next. We have an actioner that learns to essentially take actions in the environment, either navigation actions or interaction actions. And then there is a confusion model that tries to see if the agent has high confidence in performing the task. If not, then the agent will have to will decide to ask a question. So this allows us to decide when to ask a question. So then we also have an answer-aware question generator that we built based on the locations and other attributes of the objects in the scene or the agent location. So we build a lot of question-answer pairs, and then we also have an evaluator that computes a score for how relevant each of those questions is for the current state and ranks all K pairs. And then the agent samples from that distribution of top K pairs and then asks the respective question. So if the respective question is useful, so it decreases the confusion level, then we incorporate this in the state observations and we also update the actions. We perform experiments on the TEACH dataset, which is one of the datasets in the literature that contains this task completion, household tasks and simulation. And there are also 3,000 interactive dialogues available. The evaluation metrics are goal succession rate, so the ratio of goal conditions that are completed at each episode. And then there is also task success rate, which is a more constrained metric. So if you have completed all of the goal conditions, then you get a score of 1. Otherwise, if you have missed one of the goal conditions, you get 0 score. And of course, we can also have metrics that normalize by trajectory length. So we ideally want the agent to solve the task, but solve it efficiently with as little number of steps as possible. So here the baseline is just the actioner model, and the other 2 rows is our model with different confusion methods, so entropy-based or gradient-based confusion. And we can see that our method outperforms the baseline that doesn't have any question answering capabilities. Of course, you can see that in some cases the metrics are really small, but given the number of actions that you require to complete one goal and the task complexity, we find results very promising and encouraging. And our model also shows generalization capabilities in achieving gains on the unseen test split. So these are rooms that are not present during training. We also perform qualitative analysis to see when our method fails and when our method is successful. So here I have two examples. In the top row, it's the baseline without question answering and tries to perform a task. And in the bottom row is our method with the question answering. And you can see the questions that the agent asked and the answers. So we can see, so we have two examples, A and B. And we can see that for the first example, by asking questions about the position of an object, the cabinet, then the agent can successfully find the object and interact with the object. And then in the next example, we can see that the agent tries to interact with the, so here the agent here tries to interact with the incorrect object, the countertop. But when the agent asks about how the tomato is sliced, then the question answering ability helps the agent to interact with the correct object instead of interacting on the wrong object as the baseline. In terms of failure cases, we have some answers that we incorrectly extract information for. For example, the color. In some cases, our method predicts a different color for some objects. So we found that the color of the table we predicted as black, but instead it is white. So when the agent asks this kind of question, it leads the agent to approach a black object in the scene. And in many cases, we found that some questions are not well formed and could not provide useful information to the agent. So here I have how many tables are there in a laptop, and then the answer is the remote control needs to be put onto a single table. So having methods that you can devise better questions and answers and figuring out which of those are relevant for the scene are very important future components. So to summarize, we looked at the methods that are self-supervision for image classification task or text classification, and we looked at how to sample hard negatives and how to design adversarial methods for improving the robustness of self-supervised learning. We also looked at methods that use web supervision from retrieved images to summarize a lot of videos into a single coherent summary. And we also moved on to embodied learning, embodied AI environments and learning to ask questions. So when to ask and what kind of questions to ask. And then I will just summarize with two thank you slides. Here is the information for all the papers that I have presented today. I would like to thank the students first and foremost that led this work. You can find more information about my lab here, and we are thankful also to our funding agencies. Final note for the work with the video summarization, I would like to also thank my collaborators from UIUC. So I'll be happy to take questions. Thank you.
All right, time for some questions. Are there any? If you're remote and have a question, please. I think the best way is if you put something in chat, but then I can have you read it, but that way we can see it. Are there any questions locally?
One over here.
Oh, Bruce has a question.
Hi. Yeah, I'm not familiar with the task completion metrics. Could you go back to the slide with the numbers on them for the task completion?
Yes.
Yeah, so I'm not familiar with those metrics. Are those numbers incredibly low or in general, in an absolute sense? In other words, it's a really hard task and you're hardly getting anything right, or are they high or what? You know?
Yes. So here the metric is so you have to do a task. For example, boil a potato, and that involves a lot of different subtasks, right? So you have to navigate, you have to move the potato near the stove, you have to remove the cup from the pot. So there are a lot of different subtasks and actions that you have to do. So it's very difficult to complete everything perfect, right? In many cases, the numbers are actually the best in the literature, around those numbers, like 15% success rate. So that's the best that we have done in this field so far, and in this data set.
Right, but okay, but the unseen 5% success rate sounds like you're really only just starting there. I mean, that's not much of a success rate, really, is it?
Again, if it is if the success rate means that you have completed all goals at the end of the episode, and then you average across all episodes.
Well, maybe you need some different metrics that measure successes along the way or something like that.
Yes,
Subtype success.
Yeah, the problem with these data sets is that they usually don't have a success defined for sub-goals. So you only know that you have completed the higher level end goal, but there is nothing that tells you that you have completed, for example, the smaller goals, or that you're moving closer to those.
Okay, thank you.
Thank you. Better.
Okay, good question.
Hello, you said that in the video, in the video summary, you mentioned about polynomial increasing time complexity with the number of frames. Could you explain how the proposed method solve the time complexity problem and how much it reduces the cost?
Yes. So here you have to do some kind of clustering in order to select the frames. In our case, we have a pointer network, so that immediately selects frames, right? And I have a slide. Let me just find it. Yes. So we did the runtime analysis to see how our method scales now that we removed the clustering and we have the pointer network instead. And we can see that the runtime scales linearly with respect to the input frames and the summary length. So here I have a length 30, 50, or 60. So how many frames in the summary? And then I also have like query IDs. And we can see that with respect to the number of input frames, so the axis as you go towards the right, there is an increase in the number of input frames. And so we can see that we scale linearly with respect to the number of frames.
So I'm wondering, what do you think the next step of self-supervised learning? This might be a big question, but I'm wondering your thoughts on this.
That's true. So one of the things that I haven't seen a lot in the literature is I've seen some works on multimodal for video, but I think given the amount of multimodal like vision and language work that exists, there is a need for example, adversarial methods that work with multimodal data. So I haven't seen a lot of works in this space. And another thing is that these methods take a long time to run on large data sets. So most of the previous work, and at least when we were working on this paper, used to evaluate on CIIR 10 or CIIR 100. Some methods evaluated on ImageNet, but there are only a few. So we need to be able to scale contrastive learning methods better.
Thanks.
I have a question about the video summarization task. I noticed you used text and really only to make sure that the video was roughly on target. I used the title of the video. I wonder if you, because I know you're interested in multimodal things, if you see other ways that you could use video or use text to try to compensate for some problems that probably crop up in video. Like, there isn't any necessary reason that the video, that any given video is actually in chronological order, right? It could be a video that somebody edited to show going backwards or something like that. Or they could have put other things in that have nothing whatsoever to do with that particular wedding. But I'm wondering if you used a Wikipedia article that talked about this big time event or closed captioning information from them, whether you think that could help generate even better summaries in the long run.
That's true. That's a great idea for future work. So far, we only used the video titles and descriptions, but I can see a lot of work that could possibly use Wikipedia articles or some kind of summarized articles from different sources, and then try to guide the attention so that it is chronologically correct. That's actually a great idea. Yeah.
Right, because another one that occurred to me is that I might want to see the funny video.
The funny.
I want to see the funny video where I don't know, I didn't watch the wedding. I have no idea if anything funny happened, but you know, where Prince William trips or something like that. So if you could classify things, like what makes a good summary is sort of an interesting question.
So we have some work that is in fact doing video localization. So in that case, you have a query and you have a particular video, and you're trying to locate the video segment that corresponds to that query. So if you were looking to find, let's say, the funny video moments from all of these videos, and then try to summarize that, that will be, you know, a combination of video localization and video summarization methods.
Yeah, that'd be fun.
Yeah.
Any other questions from anyone here or, Hamed? Or are you making a comment, Hamed? Why don't you go ahead and make it to everyone?
So yeah, I just unmuted myself. So about this multi-video summarization, I have a question. So in text, coherency is one of the important metrics that people optimize for and also measure. Like they want to have a coherent summary. But in video, you like get part of videos from different sources, and they might have different resolutions, different like lightings and things like that. So it may look really strange. So is there any way to kind of achieve this coherency in multi-video summarization?
Yeah, we have a metric that is just encouraging to have like smooth transitions between images. I have like all the rewards here. So we have a temporal coherence reward that just looks at the visual appearances of consecutive frames and tries to make a smooth summary, meaning that, you know, if there aren't any like transitions that look weird between the frames, so if this frame looks visually closer to this and so on, so that that summary will have a better coherence reward rather than this one. But it is true that if you have multiple videos that you have different visual appearances, it's really difficult to create a coherent summary. All you can do so far is just this kind of methods. There is an opportunity for generative methods to create a visual like coherent summary from multiple videos, but I haven't seen a lot of work in this. But I think there are some works that have just started exploring generative methods.
Yeah, cool. Thank you. And as a follow-up question, so does this coherency, where this coherency used in retrieval? Like, so for example, you retrieve videos that are coherent, so you can then do a better summarization down the road. Yes,
so the whole network is trained end-to-end with reinforcement learning. So essentially, adding a frame to the summary is treated as an action, and then the full summary up until time step T is the state, and then we learn by trying to maximize the set of rewards. So the first one will be the diversity, just trying to create a summary that has diverse frames. The next one is the representativeness. So again, trying to find frames that are clusters of centers. And then the query adaptability, meaning that we need to find frames that are closer to the web images. And finally, the temporal coherence. And all of these are summarized into one reward. And then we just fine tune the parameters for summarizing the different rewards.
Very cool, very interesting. Thank you.
I left a lot out. Sorry.
Okay. Thanks.
Finally, I should note that we also have like a user study on how coherent our summaries is with respect to, let's say, different variations, random and so on.
Good to see that you beat random, right? Be very coherent. Any other? Well, if there's no other questions, that way we can give you a little break. So Ismini, I think there's another, you have another Zoom link to connect to, so we'll see you there in about 5 minutes. Okay, thank you. And so one last time, everybody, thank you so much.